Hi, today we're going to be talking about intermolecular forces and their effects on things such as states of matter. Okay, so first of all, I want to talk to you guys about states of matter. And some of this you might know, some of it you might not. But the phase or state of matter that something is in, exists in, depends upon two opposing forces. Okay, so you got the particles, and remember, a solid, the particles are like right next to each other, and they cannot move in comparison to each other. A liquid, they are right next to each other, but they can move in comparison to each other. And then a gas, the particles are really far apart, and they're flying all over the place, bouncing off each other, bouncing off the walls, and so forth. So why do certain substances why are certain substances gases at a certain temperature? And why are some liquids and why are some solids? Okay. And therefore, it really depends upon two opposing forces. One of them is the temperature of the substance. That makes sense. That's what we have come to understand. Now, remember, temperature, what we call temperature, is really the average kinetic energy of the particles in a system. Okay, so it's basically kinetic energy is the energy of motion. So it's basically how much movement those particles have, how much energy they have to move. Okay, the higher the temperature, the more chaotic and spread out the particles are. So that is going to be the outward force, as it were. Now, pushing inward, I'm just calling like there's an opposing forces that push inward, and it is basically made up of two things. I call it the attraction of the particles. Okay, and that's the main thing. How much attraction there are between the individual molecules or particles. All right, the greater the attraction, the more ordered and condensed the particles are. Right, makes sense. And also, there is the atmospheric pressure that's acting on the particles, and those act to squeeze the particles together. All right. And this explains why liquid water cannot exist in outer space. Liquids really do not exist anywhere except when there is an atmospheric pressure. Either they're solids, okay, and they will stay rigidly in place. But if they have enough energy to break free from their attraction, they would much rather be separated and be a gas. All right? It's only the atmospheric pressure that pushes down on them and keeps them close and makes it into a liquid, makes them condense into a liquid. Okay? So it's those two opposing factors: the temperature of the substance pushing out and the attraction of the particles kind of pulling them in, and the pressure pushing them in. Okay, and it's a combination of those two that determines what phase or state of matter a substance is in. All right, and now there are many states of matter. Okay, depending on your definition, I've seen as many as 27 different states of matter. The three main ones that we're going to focus on are the three main ones that exist here on Earth. Okay, at least naturally here on Earth. And those are solids, liquids, and gases. And you can see a solid, they are orderly, they are stuck together. Liquids, they're really close together, as I said, but they are free to move about. And gases, they are few and far between, and they are just bouncing all over the place. All right. So solids, usually the attraction between the particles is high, and or the temperature is low. So you can take something, just about anything you can make into a solid, okay? And the particles are held rigidly in place. Liquids are kind of in the middle. The attraction between the particles is medium, or the temperature is medium, and the particles are held close together, but are free to move about. And as I said earlier, gases, the attraction between the particles is low, and or the temperature has to be high. So the particles can be moving very quickly, randomly at high speeds, and they are far apart. Okay? Now, let's talk a little bit more about the forces that occur between and within molecules. Now, there are two terms that often get confused: intramolecular forces and intermolecular forces. Now, intramolecular forces is the attractive force that occurs between atoms within a molecule. In other words, a chemical bond, okay? And if it's in a molecule, technically it is a covalent bond, since that's what occurs in molecules. Whereas an intermolecular force, those are the forces that occur between separate molecules, okay? Between separate molecules. Now, there are two main types of intermolecular forces. There are dipole-dipole attractions, and there are what is known as London dispersion forces, or also known as van der Waals forces. Basically, both London and van der Waals, London's the name of a scientist, both London and van der Waals basically discovered this at about the same time, and therefore they both get credit, okay? So again, intramolecular forces would be the chemical bonds between like a hydrogen and an oxygen within a single molecule of oxygen, of water. Whereas an intermolecular force would be between like an oxygen and hydrogen in two separate molecules, okay? Now, first of all, dipole-dipole attraction. This is the attractive force between the positive side or charged end of one polar molecule and the negatively charged side of another one, okay? Now, dipole attractions, as the name implies, have to occur between polar molecules, all right? Between polar molecules. Now, a good example of this would be between water molecules. Now, in a water molecule, this is a polar molecule. You guys learned how to do that before, where you can draw a line, and this is a polar bond, that's a polar bond. You can draw an imaginary line that separates the negative oxygen from the positive hydrogen. Now, the positive ends of one part of the molecule will be attracted to the negative side of a different one. This is negative, this side's positive, and opposites attract. Now, this is done through what is known as electrostatic forces, okay? So it's the electrostatic forces. Electro as in electricity, and static means that they don't move anywhere. So it's a buildup of a positive force on this end and a negative charge on that end. So it's the forces between particles that are caused by electric charges. It's also known as Coulombic forces. And there's a law called the Coulombic law that basically states that the stronger the charges, the stronger the force. Duh. And also the closer they are, the stronger the force. But that's what that is, okay? So we're talking the negative of one molecule is going to be attracted to the positive of another. Now, polar molecules possess what are known as dipole moments. Now, a polar molecule, as we said before, is a molecule that has a permanent dipole moment. A dipole moment is that positive or negative end on a the positive or negative end on a molecule, on a polar molecule, where the polar bonds draw the electrons closer to one side, thus making it slightly negative, the other side slightly positive. Such as in this hydrogen fluoride, since fluorine is much more electronegative than hydrogen, it pulls the electrons to one side, thus making it slightly negative and the other side slightly positive, okay? Now, it depends, remember, dipole-dipole attraction, as you guys learned in the activity, depends upon two things. It depends both on the presence of polar bonds and upon the molecular shape, all right? Polar bonds must be present and aligned in the same direction so that the electrons are pulled more to one side of the molecule than the other. And the shape matters insofar as I said, if you can draw an imaginary line through any part of the molecule's model that entirely separates its dipole moments, then it is a polar molecule. Now, remember, the most common Shapes for polar molecules are diatomic linear with two different elements, bent, and trigonal pyramidal. If it is tetrahedral, especially if they're all the same element on all the ends, it makes it very difficult for it to be a polar molecule. All right. Now, there is a special type of intermolecular force of dipole-dipole attraction known as hydrogen bonding. Now, hydrogen bonding is an unusually strong dipole-dipole attraction that occurs among molecules in which hydrogen is bonded to a highly electronegative atom. All right. Now, what causes hydrogen bonding? Okay. Well, first of all, it's a very strong type of dipole-dipole attraction. And it occurs when a hydrogen atom that is bonded to a strongly electronegative atom. And then it is attracted to another molecule that has a lot of electrons. Now, it is the strongest of intermolecular forces, but remember, it is still much weaker than ionic or covalent bonds. Now, what actually causes hydrogen bonding? Well, hydrogen bonding, as I said, involves both hydrogen and it is attracted or attached to a very electronegative element. By very electronegative, we're talking like fluorine or oxygen, one of those in the top right-hand corner, okay? Now, looking at the electron shell models of these, let's say you have oxygen, and oxygen has, since it's in the second period, it has two layers, right? The innermost layer has 2 electrons, 1, 2, 3, 4, 5, 6, around its outermost. And in a water molecule, you would have it attached to a hydrogen where it would share a pair of electrons. And let's say we have another hydrogen here, okay? Now, because oxygen is so electronegative, it pulls and hogs these electrons greatly in this direction, thus making this positive and that slightly negative, right? But hydrogen is weird because unlike, oxygen, for example, hydrogen only has one layer of electrons. That's it. So if it gets this layer stripped away and those electrons, let's say 75% of the time go and hang out next to the oxygen, there's no layer underneath that provides any type of negative charge. Therefore, not only is it slightly positive, it's very positive, okay? And this very positive charge makes it a lot more attracted to oxygens, which have a lot of negative charge to it. It makes it a lot more attracted to oxygens in a different molecule. All right, it's because it doesn't have that inner layer, that it's just basically a naked proton, the naked nucleus that is attracted to the oxygen in the other molecules. Now, the effect that hydrogen bonding has on the physical properties of a substance is extremely high, okay? We've talked a little bit about water and how it's weird, has all these unique physical properties, okay? And this is primarily caused by the hydrogen bonding. You see, dipole-dipole attractions in general and hydrogen bonding in particular, all right, causes a huge effect on these physical properties. It increases the stickiness of the atoms for each other, of the molecules for each other, makes them very sticky. This increases the cohesion, the adhesion, the surface tension, all of these things. And something else that I don't know if we've talked about, it also greatly increases the boiling point, okay? Because in order to break apart, as we said, in order to boil or to go from a liquid to a gas, the particles have to have enough energy that they can overcome it and separate out, right? And also to overcome the atmospheric pressure pushing them in. But Because water has these hydrogen bondings, it makes them much more likely to want to stick together, which means they need a lot more energy, a much higher temperature than they normally would, in order to achieve gaseous state. And that's what this table here shows. All right, it shows different molecules that are bent molecules and so forth. And these guys, if you notice, the boiling point, because they're smaller molecules, is getting lower and lower and lower, okay? Te is the biggest, and then H2Se, and then H2S, hydrogen sulfide. And if you think about it, if you look at this trend, water should be right about here. It should have a boiling point of about negative 100 because it's so small and light. But instead of being negative 100, it's way up here at a positive 100 degrees Celsius. That 200-degree difference is caused solely by the hydrogen bonding, okay? That's a huge difference. It allows us to have liquid water, and life on Earth, as hopefully you know, depends upon the existence of liquid water, okay? So very, very important. Now, to finish off, I just want to talk briefly about London dispersion forces. Now, these are the relatively weak intermolecular forces that occur from temporary uneven distribution of electrons that induces a dipole in a neighbor. Now, these occur in nonpolar molecules, all right? Polar molecules have dipole-dipole attraction, but nonpolar molecules and also the noble gases, these have London dispersion forces, all right? And what causes them is an instantaneous dipole, like a brief boom, very briefly, just by chance, more electrons in a molecule might be on one side of the molecule than the other. Remember, electrons are flying all over the place. So just by chance, briefly, they can migrate over to one side, okay? Now, when they do that, that negative on one side repels the electrons in its neighbor molecule over here, okay? So let's say this is one molecule, and it kind of has more negative on this side than this side, right? Well, that would push the electrons around this one away, thus making this side slightly positive. This negative, this positive, very briefly, they're going to be attracted to each other. And then they're not, okay? It's just going to be a brief, they're attracted, and then they're not. And it induces that dipole, it causes that dipole in its neighbor. All right, so looking at these diagrams, you can see how, I think this one works best right here. In one atom, let's say these are noble gases, the electrons just might be more to one side than the other, thus making this side slightly negative, this side slightly positive, let's say. Well, that positive side would attract the electrons on this atom, causing that side to be slightly negative and the other side slightly positive, and it kind of is like a domino effect throughout the entire gas. And that would cause a slight attraction for each other, okay? Now, three things I want you to know about London dispersion forces. One, they are found in nonpolar molecules and in the noble gases, okay? Two, they're very, very weak compared to dipole-dipole attractions. And three, they get stronger the larger the molecule, okay? They become stronger as the size of atoms and molecules increase. Why? Well, since they are caused by the motion and movement of electrons to one side of the molecular atom, the larger the molecular atom, the more electrons, and therefore the more electrons, the greater the negative and positive charges would be, okay? They have larger, molecules have larger electron clouds, and therefore they tend to have stronger London forces. And this goes, you can see this illustrated in the freezing points of the noble gases, okay? These are very small numbers, yes, But if you notice, the largest one, xenon, has the highest freezing point, okay? Whereas helium, the smallest, has the lowest freezing point. Now, theoretically, there shouldn't be any difference. But because xenon is so big, it has, I don't know, like 119 electrons around it. When they go to one side, they form a much stronger negative charge, okay? Therefore, there would be a much stronger London dispersion force. All right? So nonpolar molecules, very weak, but it gets stronger the bigger the molecule. All right? So hopefully this made sense. And if you have any questions, please ask during tutorial. Bye-bye.